colleagues, my name is Ambuj Tiwari and we were discussing the chapter reaction mechanism. And today's topic is nucleophilic substitution reaction. Today's topic is nucleophilic substitution reaction. So, we will be discussing two types of nucleophilic substitution reaction, that is SN1 and SN2. Starting with SN1 reaction. So, what is a nucleophilic substitution reaction? Nucleophilic substitution reaction is a reaction in which an atom or a group is replaced by another atom or a group. For example, in an SN1 reaction, this S stands for substitution. This N stands for nucleophilic. And this 1 signifies that this reaction is a unimolecular reaction. So the next question which raises in front of us is, what is a unimolecular reaction? We'll discuss this. A unimolecular reaction is a reaction in which the RDS step, that is the rate determining step, contains only single molecule. That is a unimolecular reaction is a reaction in which RDS, rate determining step, involves only single molecule. So let us discuss the mechanism of SN1 reaction. In SN1 reaction, let's suppose the initial molecule is alkyl halide. We will be discussing all the three molecules that are alkyl halide, alcohol and ether one by one. So the first one which we will consider is alkyl halide. In alkyl halide, let's suppose this Rx gives us our nucleophile when reacted with a nucleophile. So in mechanism we will see that SN1 is a two-step process. In the first step, this Rx breaks into two parts, giving us a carb cation and a negative halide X minus. In the second step, this carb cation is attacked by a nucleophile, giving us our nucleophile. Now, at this point, I want to remind you that this nucleophile need not to be a negatively charged species. We generally denote it by this symbol, but it doesn't need to be negatively charged. We will discuss the examples of this reaction in the coming time, and let's discuss the characteristic of SN1 reaction. The first one is, it's a unimolecular reaction, as explained earlier. In the rate determining step, only a single molecule is involved. The second one is, it's a two-step process. As discussed just now, in the first step, the carb cation is formed, and in the second step, nucleophile is attacked by this carb cation. And the third one is rearrangement. As we have seen, it's a two-step process, and in the first step, we get a carb cation intermediate. So, this carb cation can undergo a rearrangement to form a stable carb cation. We'll discuss this point in detail further. And the fourth one is the kinetics of this reaction, which is, it's a first order reaction, and the rate depends only on the concentration of alkyl halide. That is, the rate of this reaction depends only on the concentration of alkyl halide, that is Rx. After discussing the characteristic of SN1 reaction, let us discuss the energetics of this reaction. So, we have earlier mentioned that the mechanism of this reaction is, in the first step, Rx, let us make this in 3D. Let's say it's a deuterium instead of hydrogen, just to distinguish. And this is the R molecule, and here we have a leaving group, let's say X, any halide. So, in the first step, this halide leaves the molecule, giving us a carb cation intermediate, which is planar in nature, that is R H D. Now, it is a planar species. That is, the coming nucleophile can attack on either of its face. For example, if it's a planar molecule, the nucleophile can attack from upside, or it can attack from down. So, it will give us two corresponding structures. The first one will be R H D, and the nucleophile will be on this side, or the nucleophile can be on the opposite side. Let's make clear by drawing it here. This is a possibility, and the other possibility is the nucleophile is on the other side. So we can clearly see we have a racemization. Both these are enantiomers. So we'll discuss this reaction in light of this mechanism. This is a two-step reaction. The first step is making of planar carb cation species, which can rearrange. This can rearrange itself to form a stable carb cation. And the second is a very quick step. This step is the rate determining step, RDS, which involves only a single molecule. Hence it is called unimolecular reaction. And the second step is a fast process in which nucleophile attacks on the planar carb-cation species and forms two products depending upon the attack, whether it's from upside or downside. So now we'll discuss the energetics of SN1 reaction. We'll discuss the energetics. So let us consider that we have reaction coordinates on the x-axis. We can monitor a reaction by, let's say, time, and here is the energy. So let's say this is the initial energy level of Rx molecule. First, we will need to provide some energy. This will be the energy profile of a reaction. This is the Rx initial reactant, that is alkyl halide. This is the final molecule, or nucleophile. These are the two transition states that we have with us. So the first one is departure of alkyl halide. See, this bond is being broken, and once this energy barrier is crossed, we'll get a stable carb-cation intermediate in this value. And this second relatively lower barrier, which will definitely be crossed if this greater barrier is crossed, is the formation of a new bond between R and nucleophile. So these are the two transition states. This is transition state 1, this is transition state 2, because this is the two-step processes. So we will have two transition states. This is delta G of the reaction, that is the energy difference between reactant and final product. These can be considered as energy of activations delta G1 and delta G2. Clearly, if we have sufficient activation energy to cross the first barrier, the second barrier will not matter at all. It will definitely be crossed. So we say that the first step is the rate determining step. If we however cross this first step, then the second step will be a fast step and will not hinder reaction. So this is the energy profile of a reaction. This is the initial product alkyl halide. This is the final product. This is the transition state 1, transition state 2. Here in transition state 1, this Rx bond is being broken. In second transition state, R nucleophile bond is being made, and in this valley we have a stable carb-cation intermediate. Now we'll see the factors which will affect all these peaks. We'll try to make this peak lesser, so the energy of activation needed will be less. We'll discuss this in further detail. After energetics, we'll also discuss the stereochemistry. Stereochemistry of this reaction. Stereochemistry is the spatial arrangement of atoms around the central atom. For example, we have H, D, and let's say R, X. The carb-cation formed is a planar species, thus it will give me a planar molecule. This can be attacked from either phases. So the product we will form will be a racemic mixture of D plus L. Now, here is a thing which we have to know. This is true only if this R part is considered to be non-chiral. Suppose if this R is itself a chiral molecule, then instead of getting enantiomers, as discussed in this case, we'll get diastereomers. I'll discuss this in detail. For example, I have this molecule C X H D, and the carbon attached to the alkyl halide carbon is also chiral. That is, it has some 3 different groups attached to it. Let's say R1, R2, R3. So now we have, let's say this configuration is R and this is S. After SN1 reaction, this S will be racemized. That is, and the thing to notice is that this carbon is untouched. So its configuration will also be untouched. If it is R initially, it will remain R in both the cases. That is, after racemization, we'll get 2 products. Let's say H D, and nucleophile in this case is here, and this carbon is still the same, that is R, R1, R2, R3, and the configuration is still R because this carbon is untouched. And in the second case, this will remain R, and let's say if it is R in this case, then it will be S in this case. Nucleophile D, H, and the same R1, R2, R3. So it can be clearly seen that these 2 molecules will not be enantiomers, they will be diastereomers. Diastereomers are the one in which if there are 2 chiral centers and the configuration of only one is changed, that is, this R remains R and this R is converted into S. The enantiomers will be if both these R are converted to S, but this is not the case. So these 2 molecules will be diastereomers in this case. This is a very, very crucial point to know. After discussing stereochemistry, we'll discuss the factors affecting the SN1 reaction. That is, factors affecting SN1 reactions. I told you that we will be discussing how to stabilize the carb cation in the energetic diagram. So we'll try to stabilize the carb cation, increase the leaving group ability. So let's discuss all those factors one by one. The first one is the structure of substrate. By substrate, I mean alkyl halide in our case. That is the reactant. Okay, let's see how the structure of alkyl halide will drive the course of reaction. Let's say this R, which is our substrate in this case, is a 3-degree molecule. So, the carb cation formed by it will be a 3-degree carb cation. And as we know that 3-degree carb cations are very much stable than the corresponding 2-degree or 1-degree carb cation. Hence, in SN1 reaction, the 3-degree alkyl halide will be very much reactive than 2-degree, and the 1-degree carb cation is very less reactive, or we can say almost unreactive by SN1 reaction. The other two molecules which we want to discuss here are benzylic carb cation and allylic carb cation. So the benzylic carb cation is the one in which we have a carb cation just near this benzene ring, and this carb cation will be stabilized by the mesomeric effect of these bonds. Hence, this will be a very stable carb cation instead of being only 1 degree. If you see, it's a 1 degree carb cation, still it will get the mesomeric effect of benzene. Hence, it will be a very stable carb cation, even more stable than the 3-degree carb cation, because mesomeric effect is a very strong effect, and same is the case with a allylic carb cation. Here, this will be stabilized by the mesomeric effect of this double bond, making it much more stable even than 3-degree carb cation, even if this is only a 1-degree carb cation. So, the final order we have is the benzylic and allylic alkyl halide are almost equally reactive, but both are greater than 3 degree, which is greater than 2 degree, and which is in turn much greater than 1 degree. This one is very less reactive, or we can say it's unreactive via SN1 mechanism. So this is the order of substrate. Remember, here we are talking about R. What is R? If R is benzylic, R is allylic, R is 3 degree, R is 2 degree, or R is 1 degree. So this will be the order. The second factor which we'll be discussing is the concentration and strength of nucleophile. Concentration and strength of nucleophile. So, if we think a little, we can find that in the SN1 reaction, nucleophile attacks in the second step which is a very fast step and is not our rate determining step. Even when we found that in kinetics, rate is only proportional to the concentration of alkyl halide. So, it's clear that the concentration of nucleophile doesn't matter. If you increase the concentration of nucleophile, it will not increase the rate of the reaction. And even if you increase the strength of the nucleophiles, it doesn't matter for SN1 reaction. So the point to note is the concentration and strength of nucleophile doesn't matter in SN1 reaction. The third point, which is very important to discuss, is the solvent effect. This plays a very tremendous role in SN1 reaction. Suppose we have a polar protic solvent, that is, it has H plus. Let's say H2 is one of the such solvent. We'll take the example of H2 and explain the solvent effect in case of SN1 reaction. So, in our reaction, the first step, we have Rx converted to R, that is carb cation, and a negatively charged halide ion. And this is the rate determining step. So, for this reaction to go in forward direction, we need to stabilize R plus and X minus. The best way to stabilize them is to have a polar protic solvent. Let's see what a polar protic solvent can do for us. So suppose we have a R plus species and H2 as our solvent. We know oxygen has lone pair electrons. It can stabilize our R plus by donating these lone pairs. So these water molecules will form a shell around R plus, making it stable. Hence, this polarity is used, this delta negative charge is used to stabilize this carb cation. This is the part where polar comes in the picture. This is the part where polar comes in the picture. Now let us see how this protic thing helps us. Let's say this is our negatively charged halide ion. This will be stabilized by the protic. That is, it has delta plus, it has delta minus, and this negative charge will be stabilized by this delta plus. So, like this, it will form a shell in a similar manner. There will be one more. So see how beautifully it stabilizes our negative charge by making a shell around it. So here comes this protic thing into the picture. Hence, a polar protic solvent is very useful in an SN1 reaction. Sometimes the effect is so tremendous if we make this polar protic solvent into non-polar aprotic or even polar aprotic solvent, the reaction vanishes. It doesn't happen at all. The fourth factor which is considered in this discussion is the leaving group availability. So let's see how do leaving group availability, or we can say leaving group ability. helps us. We remember that the first step is the formation of carb cation and a negative charge halide. This is the RDS, redetermining step of our SN1 reaction. So we have this R plus carb cation species and this X minus species. So the easier this bond breaks, the easier these products are formed. That is, the better this X is a leaving group, the better this product is formed and the faster the reaction is. So if X is a good leaving group, SN1 rate increases. We can see the rate which is I minus, Br minus, Cl minus and F minus. This is the leaving group rate as discussed in the previous video of halides from alkyl halide. So we can say that for the same R, Ri will be the fastest, then Rbr, then Rcl, then Rf. For the same R, this will be the order of the rate for SN1 reaction. So let me recapitulate all the four factors that we have discussed. The first one was structure of, okay, let me start from this corner. Structure of substrate, which was benzylic, equivalent to allylic, 3 degree, 2 degree, 1 degree. The second was the strength of nucleophile or concentration of nucleophile. So our verdict was it is independent of this. The third one was solvent effect. We have seen that polar protic solvent is required for SN1 reaction, and the last one was leaving group ability. These were the main four factors that will direct the reaction. The rate will depend on these four things. And now we will discuss some examples of SN1 reaction. Examples for alkyl halide. So, if we have a tertiary alkyl halide, let's say CS3, 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 Br in presence of H2O. So, the first step will be formation of carb cation. The carb cation will be formed. And this Br minus will be stabilized by these water molecules. The second step will be attack of nucleophile. Now we have two choices. The first one is to use water itself as a nucleophile, because in an SN1 reaction the strength of nucleophile doesn't matter. So this neutral water molecule can also act as a nucleophile, will attack here and form an alcohol CH3, 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 and this will be OH. Or the second choice is have a separate nucleophile which will be, let's say, another alcohol ROH. For example, we take MEOH. So these oxygen lone pair are available to attack, and this will form an ether molecule CH3, C, CH3, CH3, O, and this will be R group, which in this case is methyl. So these are the two very generalized examples. Now we will have some very specific examples of SN1 reaction. The most important example which we need to discuss here is an example in which we have a rearrangement. CH3, CH3, CH. Let's say we have a alkyl halide CH2Br, and this is a H. So at first look, this doesn't satisfy our criteria because 1 degree carb cation are not stable at all, so they shouldn't react. But on taking a look, if we see this carb cation has a special opportunity, that is, suppose this Br leaves the molecule and this carb cation is formed, then the opportunity is to have a hydrogen shift. That is, this hydrogen will be captured by this carbon and this carb cation will be rearranged. So we got a 3 degree carb cation, which is very favorable, very stable. Thus, this reaction will have a rearrangement. And then you can react it with any nucleophile, let's say OH2, that is water, or any alcohol, and it will give the corresponding product, let's say water. Then the product will be CH3, 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 and this will be OH. So this was the specific example that will give us an idea how the rearrangement is done in SN1 reaction. So we have come to the end of our alkyl halide molecule. We have discussed most of the aspects, the factors affecting the reaction,